All right, let's dive right in. We're going to the very edge of physics today to tackle a question that sounds simple, but is, well, it's profound. Is there a cosmic weight limit? You know, a point where something gets so heavy, so dense, that it just breaks reality? We're going to find out. So, picture this. A star, way, way bigger than our sun, has just died. It's run out of fuel, gone out in this huge, spectacular explosion. And what's left behind? Its core, crushed by its own immense gravity into one of the absolute weirdest objects in the entire universe. And this is the core of our mystery today. There has to be a limit, right? A point where this stellar corpse just gets too heavy, and reality itself kind of gives up. So what is that cosmic weight limit? So, what are we dealing with here? A neutron star. And you really got to try and wrap your head around this. Imagine taking the entire mass of our sun, we're talking 333,000 Earths, and crushing it all down into a ball the size of a single city. The density is just staggering. A single spoonful of this stuff would weigh billions of tons. Billions. Okay, so with all that insane mass and that unbelievable gravity trying to crush it, what's holding it up? This is the exact puzzle that a few physicists, J. Robert Oppenheimer, George Volkoff, and Richard Tolman set out to solve way back in 1939. They knew some force had to be pushing back, but the big question was, could it push back forever? Now, to figure this out, they realized pretty quickly that the normal rules of gravity just weren't going to cut it. You know, the stuff that works for dropping an apple or keeping the Earth in orbit around the sun? Nope. For an object this extreme, they had to pull out the big guns. Albert Einstein's general relativity. See, Newton's gravity is pretty straightforward. It's a pull, a force. But Einstein saw it totally differently. For him, massive objects literally bend and warp the fabric of space-time itself. And for something as ridiculously dense as a neutron star, that warping is so extreme that Newton's math just completely falls apart. And the original physicists, they knew this was non-negotiable. Trying to use Newton's laws on a neutron star would be like trying to use a city map to navigate across the ocean. You have to use the right tool for the job. And that meant using Einstein's equations to account for how gravity was warping space and time itself. So how in the world do you study the inside of an object you can never, ever visit? Well, you build it on paper. Oppenheimer, Tolman, and Volkoff created a theoretical model, a star built not out of matter, but out of pure mathematics. It was their own little theoretical laboratory. Their first step was to simplify things. A lot. They imagined the core of the star was a sphere of perfect fluid, which is basically a fancy way of saying a perfectly uniform, frictionless ball of stuff. This brilliant simplification meant they could actually apply Einstein's equations to calculate the two forces at play, gravity crushing everything inward and the pressure of the star's guts pushing outward. So here's how their little paper experiment went. First, imagine that perfect sphere. Then you have to define its properties. Basically, you set a rule for how much it pushes back when you squeeze it. It's called an equation of state. With that rule in place, they just let Einstein's equations do the heavy lifting, calculating the crushing force of gravity. They were looking for that exact point of balance, the tipping point. And after all that mind-bending math, their models spit out an answer. And it wasn't just a vague idea. It was a single, crucial number. A cosmic tipping point, beyond which a stable star was just impossible. You see, their model didn't just show that there was a balance. It showed exactly where that balance breaks. They calculated the precise mass where the inward crush of gravity would simply overwhelm any possible outward push from the neutrons inside, a point of no return. And the number they landed on? About 0.7. That's it. Just 7/10 the mass of our sun. According to their 1939 calculations, any dead star, any neutron star heavier than that was absolutely doomed to collapse. This became known as the Tolman-Oppenheimer-Volkoff limit, or the TOV limit for short. Now, to really get why this was such a big deal, you have to look at what people thought before. Earlier models, using good old Newtonian physics, predicted a limit way up around 6 times the mass of the sun. The TOV limit was nearly 10 times smaller. It just shows how much gravity's ability to, feed on itself really matters. Now, modern observations have pushed that limit up to about 2.1 solar masses. So why the difference? Well, their perfect fluid model was a bit too simple. It didn't account for the strong nuclear force, which gives the neutrons an extra pushback. But here's the key takeaway. The revolutionary part wasn't getting the number exactly right. It was proving that a hard limit existed in the first place. This mathematical limit, it wasn't just a number. It was a prophecy. It was a description of what happens when the most powerful force in the universe wins the fight. Completely. So this is it, the ultimate implication of their work. If you have a dead stellar core that weighs more than this limit, say 2, 3 times the mass of our sun, what happens to it? Where does it go? The answer from their equations was terrifyingly simple. Nothing. Nothing can stop it. No force in nature that they knew of could halt the collapse. Gravity doesn't just win, it achieves total, absolute, unstoppable victory. The collapse just keeps going and going. And right there, buried in the math, was the birth of the modern black hole. An object so massive and dense that it collapses past that point of no return, warping spacetime so severely that it becomes a trap from which nothing, not even light itself, can ever escape. Honestly, the legacy of this 1939 paper is just monumental. It was the first time anyone had a rigorous mathematical argument that black holes must exist. It took them from being this kind of sci-fi concept and turned them into an inevitable consequence of the laws of physics. And that just leaves us with a final thought, doesn't it? Back in 1939, a few pages of math predicted the existence of the most mysterious, most extreme objects we've ever found. It really makes you wonder, what other cosmic secrets, what other universe-bending truths are still just hiding out there, waiting to be found, in the language of mathematics?